This is the vertebra of a plesiosaur. It's 160 million years old and it was found in Peterborough. Now, in case you'd forgotten, a vertebra is a bone in the spine, and plesiosaurs were a group of marine reptiles which lived from the Triassic all the way through to the Cretaceous when they became extinct along with the dinosaurs and the pterosaurs. Now, something very unusual, I thought anyway, about this vertebra of a plesiosaur is that it seems to have these very unusual, perfect round holes in, almost to the extent which I thought someone had drilled into it, or it was a fake or something, but actually it turns out these holes are very real, they're meant to be there, and they tell us a lot about how plesiosaurs lived. When I first saw these holes, I thought the logical thing to do is to take it to an expert. So I went to the Charmouth Heritage Centre, where there are some friendly paleontologists who can help you out with your inquiries, and I said, "What are these holes?" They didn't know. So they got out a little identification book, and I learned 3 things from this. So first of all, these holes are unique to the vertebrate of plesiosaurs. They help you identify it. Secondly, not only are they unique to the vertebrate of plesiosaurs, but they're unique to the cervical vertebrate of plesiosaurs, that is, the neck bones. Reminder of spinal anatomy: you have the cervical vertebra, which is your neck, you have the thoracic vertebra in your chest, your lumbar vertebra in your abdomen, and your sacral vertebra in your pelvis. Now, we have 7 cervical vertebrae, and so do all mammals actually, even giraffes, even though they are stretched out a bit. Sauropods, those long-necked herbivorous dinosaurs, they could have about 20 vertebrae, but plesiosaurs, they could have way more, like over 35, and some of them, like Elasmosaurus, could have pushing 70, so that's a lot. The neckiest necks that I've ever necked. The third thing that I learned from the book is that it identified these holes in the vertebra as nutrient foramina. What are nutrient foramina? Well, foramina is the plural of foramen, which is basically a hole in a bone through which something passes through, usually nerves or blood vessels. A nutrient foramen contains the nutrient artery, that is an artery that supplies the ossification centre of that bone. That is where the bone actually started becoming bone. So I asked, well, how do you know this is a nutrient foramen? And they said, well, we don't really know. So I thought, oh, this must be why Michael Gove said that the country's sick of experts. So I did the logical thing and I consulted a more expert. And I did that by doing a bit of a literature search, and I found that someone had investigated this very question in 2017. They'd done a micro CT scan of the plesiosaur vertebra, and they'd done a few histology slices as well. And they'd found that actually it doesn't seem like it is a nutrient foramen, because a nutrient foramen, as I said, you'd expect to end in the centre of the bone, to the bit of the bone it was supposed to be supplying nutrients to. But actually, this canal passed all the way through the holes at the top to the holes at the bottom. It was what was known as an intersegmental artery. And we have intersegmental arteries in our vertebrae. The thing is, those aren't retained into adulthood. So the point of an intersegmental artery is to create an anastomosis, that's the posh word for a connection between 2 vessels, an anastomosis between the spinal artery and the vertebral artery. Now, let me explain a bit about anastomoses in this area. In humans, as with most mammals, we have a dual blood supply to the brain. That is, we have an anastomosis between a vertebral artery and a carotid artery, as you can see here, the carotid being at the front and the vertebral artery being at the back. And that enables us to have a nice good blood supply to our brain. But actually, this is a bit more of an exception than the rule when it comes to the animal kingdom, because most animals don't have this dual blood supply to the brain. Most animals just have the carotid artery supplying the blood. The big question then is, why did the plesiosaurs retain the intersegmental arteries into adulthood? What purpose did it serve, if any at all? One of the ways we can investigate this question is by looking at animals alive today that have similar adaptations. There is a group of animals that do retain anastomoses between the spinal artery and the vertebral artery, as we found in the plesiosaurs, and that is a group of tree climbing snakes, and the one that's been studied is called black rat snake, or Pantherophis obsoletus. Now, it did used to be called Elathi obsoleta before a bit of phylogenetic analyses in the noughties split that genus up a bit. Turns out that if you measure the blood flow of the vessels in a snake's neck, you will find that the black rat snake has anastomoses between the spinal artery and the vertebral artery, and in the paper where they investigated this, they did put it down to gravitational pressure, because you know this snake climbs trees. You know when else puts you under a lot of pressure? Yep, diving really deep down underwater like a plesiosaur looking for something to eat. Remember that the water pressure increases by a whole atmosphere of pressure for every 10 metres down that you go. So it might be that these intersegmental arteries helped plesiosaurs dive. You see, if you've got a vessel in the middle of a bone, that bone's going to protect that vessel from high pressure, isn't it? One way to test whether we're right with this is to look at other animals that dive deep down. Sperm whales, the deepest diving mammal known to science. The reason they dive down so deep is because that happens to be where their favourite food is, the giant squid. Let's take a sperm whale skeleton. You look at the neck, it's very short and stout, and that's because it turns out that having a long thin structure under pressure means it's going to get squished. So sperm whales don't do that, they have almost no neck. The other thing to notice is that the whole whale itself is like that. Now let's have a look at the vascular system of the whale. Now, no one has been able to study the vascular system of an adult sperm whale because they're too big, but you can study the vascular system of a fetal sperm whale. So let's look at that. Look at the neck, loads of anastomoses there, whole big network, because it's very important that the brain gets a lot of blood. Under pressure, that's difficult to achieve. So that's sperm whales. Now let's have a look at giraffes. So giraffes, as I said before, they have 7 cervical vertebrae just like us. So it's not actually that good an analogy with a plesiosaur, but it will do anyway. Gravity is a challenge when giraffes are trying to pump blood all the way up there to the brains. However, they deal with this by having a very high blood pressure, 300 by 180. 300 by 180 is twice that of a human with stage 2 hypertension, that is. So not exactly normal. And the way they do this is by having valves in their jugular veins, and then also having a big fascia pressure suit all around the vessels across their body, and that keeps blood where it's supposed to be, and that means they don't pass out. In summary, those holes in the plesiosaur vertebrae were the canals for an intersegmental artery, which provides an anastomosis between the spinal artery and the vertebral artery, therefore enabling blood flow to the brain despite the high pressure exerted by the water when the plesiosaur was diving. It's an adaptation to diving, we think.